All right, let's talk about chapter 4 here, dynamics and Newton's laws. Okay, so we're going to talk about what a force is, okay, and then Newton's first law of motion, the second law of motion, and the third law of motion, and then go into some examples of applying these three forces together. So Isaac Newton built upon what Galileo came up with in terms of these laws of motion, and he realized that the reason that the moon orbits the Earth is because of a force of gravity, and it is constantly falling towards the Earth. That was the idea with Newton sitting under the tree. The apple hits him on the head. He realized, oh my gosh, the same force that pulled the apple down onto my head is the same force that keeps the moon in the orbit of Earth. Okay, so that led to his laws of motion, thinking about that problem. So let's start with the concept of a force. So we've got a person here. We've got one person pushing on them that way and one person pushing on them that way. So just because we draw the arrow pushing on this person like that, we can do the same thing, have the arrow come from the person like that. So just because the force is pushing this way, we can draw it either starting there and going forward or starting here and going forward. Either way, whatever's easier for you to conceptualize, it doesn't matter. So, and just like we take this force here, we can move it over there, boop, and do our head to tail method and add these two vectors head to tail. So we've got our two force vectors here and here. Okay, grab this one, put it there, okay, or grab this one and put it there, and that's what they did here to show that the force this way and the force that way add together. So you're pushing here, pushing there, your net force is going to be that way. Okay, so that's what these dotted lines are the head to tail method of adding the two vectors together. And again, how does that work? It's the x component of this plus the x component of that. So it's only this, that's the only x component because there is no x component in F2. And then there's no y component in F1, so the y component of your net force is just F2. They just add together nicely. So then there's your net force, okay? Add those two things together. This picture is called a free body diagram, okay? And that's where you draw the forces at a point to figure out what the net force is. So you add up all the component forces to get you a total force. There's another type of force here called a restoring force, and that's an example like a spring. If you pull on a spring and you let go, it'll slingshot back, and that's the idea. As you pull a distance, you'll get a stronger force pulling against you. That's called a restoring force, and we'll talk about that force later. Okay, so Newton's law of motion says that an object in motion stays in motion unless acted upon by an outside force. Okay, so a body remains at rest or in motion, remains in motion at a constant velocity unless acted upon by a net force. So that means when you're on a hockey rink and you get going and you start sliding, nothing is going to stop you, okay, unless an external force stops you. So you will continue at that speed until you hit the wall or you hit something, or you figure out how to apply enough friction between the skates and your and the ice rink to steal some energy from you. Okay, so that's the law of motion, and that's important because the moon is going to continue to orbit the Earth indefinitely until something stops it, right? So that's where that law comes from. What keeps the planets in motion? Well, nothing is stopping them, so they have to stay in motion. Okay, so this property that allows something to remain in rest or in motion is called inertia, and it's just mass. When you talk about the number of kilograms something has, what you're talking about is its inertia. The heavier an object is, the harder it is to get it to move, and the harder it is to stop it if it is moving. Okay, how about this? Which has more mass, a kilogram of cotton balls or a kilogram of gold? Since they are both 1 kilogram, they are the same. Okay, you might have a different volume or something like that, but if you have the same mass, you have the same mass. It's just as hard to stop a kilogram of cotton balls as it is to stop a kilogram of gold. Okay, so the second law of motion is F equals ma. When you do apply a force to something, F, you get an acceleration, and it depends on its inertia. F equals ma. The more inertia an object has, the harder it is to get going. The bigger the force you need for the same acceleration. Okay, so acceleration is a vector, force is a vector. Whatever direction the force is, the acceleration is going to be in that same direction, but the length of the acceleration vector will change because we're multiplying that vector by a scalar. Okay, so our acceleration vector here will be in some direction, and whatever the mass is, we can shrink or lengthen that acceleration vector. The smaller the mass, the bigger the acceleration, for example. Okay, and then, because actually what we're doing is dividing the force by the scalar. Okay, let's see. Yeah, okay, so we've got an example here. A couple folks pushing on a, looks like an adult. There should not be an adult in that cart. I think it's supposed to be a child, but they didn't. Yeah, that's sad. Okay, so anyway, they're pushing on this wagon. All right, and then we got a lot of arrows here. What the heck is this? Too many arrows. Look at all these arrows up and down and every which way. Okay, so this is an example of trying to describe the motion on an object. If we can figure out the net force, if we can figure out the resultant vector of all these forces added together, the sum of all those forces will give us our acceleration. Okay, so we draw what's called a free body diagram to simplify all this stuff into something a little easier to understand. So what do we have? We have the wagon, or the kid in the wagon, and we want to know what's the acceleration on the kid. So we have to add up all the forces. So there's a couple forces here that don't matter, and one is called the weight, and the other is the normal force, and we'll talk about those in a little bit, but they are equal and opposite, so they cancel out. We don't care about them. There's no acceleration in the up or down direction. That's what that means. Okay, then there's a force of friction here that you have to overcome. But then you've got two kids here pushing. One is pushing with F1 and one is pushing with F2. Those two forces will act together, F1 plus F2, and then our net force then is going to be F1 plus F2, because those are going to act together, and then minus whatever this force of friction is, and that will give us our net acceleration. So we'll divide all this by the mass, and then that will equal our acceleration. All right, so what is an example of this? We would have to know that this was 10 newtons, for example. This was 13 newtons. Well, this would be more like, judging by the scale of them, let's make this 10 newtons and this be 2 newtons. So then we'd have 12 newtons in the positive x direction, but then let's say there's a force of friction of minus 1 newton here. So then we'd have 10 plus 2 minus 1 equals 11 newtons, and that would be our net force. Okay. And then we've got another example here where you just have one person pushing on, so we only have one force, but it's a bigger force because it's an adult pushing on an adult child. Okay, so you push on the wagon like that, boom, and the length of that vector is the strength of the push, and you've got the same negative in the opposite direction, and so your net acceleration, again, your net force gives you that net acceleration. Okay, so that's what you're going to be doing with these problems. You'll be drawing a free body diagram, adding up the forces in the x direction, and then solving for the acceleration. That's it, by dividing by m. So you're doing everything you did before. You're adding vectors, subtracting vectors, whatever you need to do, only in 2 dimensions, and then calculating the force, okay, or the acceleration. And so there it is, F equals ma. That's Newton's second law of motion. Newton's second law says F equals ma. The net force on something equals the acceleration. The force, the unit of force, is a newton. And if you ever forget what the force is, what the units are, F is equal to ma. Well, you know that mass is kilograms and acceleration is meters per second squared. So then a newton is a kilogram per meter per second squared. 1 kilogram meter per second squared. Yeah, that's what 1 newton is. And that's how you can remember what the unit is, because if you see newtons somewhere and you want to divide by kilograms or something, then you're going to have to know what its units are and replace the newton. So we put n there because it's easier than drawing this all the time. but you have to know that this n represents those units, okay? All right, so F equals ma. The first law says an object in motion stays in motion unless acted upon by an outside force. Second law says if you do get a force acted on you, you will accelerate, and that will change your motion. Okay, so that's how the second law is linked to the first law. Then we've got a new introductory thing here. It's called weight. It's a vector. Weight is just your mass times gravity, 9.8 meters per second squared. So a 1 kilogram object would experience a force of 9.8 newtons on it, which is what causes it to accelerate, 9.8 meters per second squared. When an object, when the external force on an object is its weight, we say that it is in free fall. So if an object is in free fall and the only force on it is the force due to gravity, we call that weight, and weight is equal in quantity to mass times the acceleration of gravity, the mass of the object times g. Okay, so the heavier an object is, the greater the force on it, but the heavier it is, the more inertia it has, so it cancels out. Whenever you have F equals mg, you have a bigger force for a bigger mass, and they're in proportion to each other by this gravity thing. So the bigger your force is, the more mass you have, the bigger your force is, and the proportionality, the constant, is g, 9.8 meters per second squared. Okay, mass versus weight. This is an important thing. Weight is different. You go onto the moon, you go onto Mars, you're going to have a different weight because the acceleration of gravity on those planets will be different. But your mass, the amount of atoms that are in you, is the same whether you're on the moon or Mars or whatever. So don't get confused by mass and weight. Weight is a force, mass is a scalar, mass is a quantity. Okay, so this is an example. You push on a lawnmower with some net force, and the question is you apply a net force 51 newtons, and the mass of the mower is 24 kilograms. What's the acceleration? That's easy. F equals ma. We apply a 51 newton force. It's a 24 kilogram thing. F equals ma, so F over m is a, and the acceleration then is 2.1 meters per second squared. So that's just an example of applying a force to something that has a mass. You divide by the mass to get the force in terms of acceleration. Okay, we've got another example here. We've got 4 thrusters pushing on this thing and some small coefficient of friction here. And then we have our normal force and our weight force canceling out, so we're going to ignore them for now. So our free body diagram on this thing, we're going to have 4 vectors added together because we have 4 thrusters, and then just one little tiny friction thing taking away some of that. So our net force then is going to be 4 times the thrust minus this tiny friction force, and they tell you what all those things are. Sorry, it tells you what the acceleration is, so then you can solve for what the thrust is. Okay. Newton's third law of symmetry. So what Newton's third law says is for every action there's an equal and opposite reaction, again related to the first two. First one says an object in motion stays in motion unless acted upon by an outside force. Second law says F equals ma. If you do apply a force, it will change your motion according to F equals ma. The third law says if you do something, whatever you do will be done back against you. The same force will be applied to you. Now the difference is, since things have different masses, you're going to have different accelerations even though the forces are equal and opposite. So for example, the swimmer here applies a force to kick off the swimmer applies a force against the wall, but the wall applies the same force back against her. Okay, and the difference is the mass of this wall is like infinity, or may as well be. It's a huge concrete thing. The mass of her is negligible compared to that mass of that wall. So that means when she applies that force, she can actually get the wall to push back with that same force, and that allows her to accelerate because her mass is so much smaller. So what do I mean? I mean F equals ma. So if I apply F to this mass of this giant wall, so let's say I apply 20 newtons of force against the wall, and the wall weighs 1,000 kilograms times acceleration. The acceleration of the wall when I kick off of it is going to be 20 newtons divided by 1,000 kilograms, so that's going to be 0.002 meters per second squared, right? 1, 2, 3, yep, okay. Whereas if I apply that same 20 Newton force and I only weigh, 50 kilograms or something, 60 kilograms times acceleration, then the acceleration of me is 20 over 50, which is, 2/5 meters per second squared. So I get an actual, acceleration here that's measurable by applying this force to the wall, whereas the wall is going to have a negligible acceleration. It's not going to even appear to move, and the wall actually weighs a lot more than 1,000 kilograms, probably 20,000 or something. Actually, you have the whole Earth that you're trying to push against when you kick off a wall, usually because it's anchored to the ground. Okay, so that's an example of how the same force, 20 newtons, will give you a different acceleration depending on your inertia. Okay, so that's what it means by every action has an equal and opposite reaction. Okay, so whenever you push on something, it pushes back with the same force, but that doesn't mean you're going to get the same acceleration. So that's the idea. Okay, so again, another example. You've got a professor pushing on a cart system. So this is trying to emphasize that there's a couple of different ways to calculate the net forces. You don't want to draw all of these forces, the force of friction and the push force of the floor with the push on the cart and the friction and everything, because you want to describe the net force on the net object motion. So if you push on the cart here and there's a friction there, that's going to be your system. If you want to talk about pushing off the ground this way and that balancing out with our force of friction, then that will be our system, and we'll ignore the push on the cart because this is encoded with that force down there. So that's what that's trying to show, is that you could set up two free body diagrams, one for system 1, one for system 2. You should get the same answer depending on what's going on. Okay, so that's just an example. Let's see here. And yeah, we got a force on the cart, and they're just showing you the different things. Okay, so 4.5, normal tension examples, other examples of forces. So we have a weight. Now, if you're in free fall, then the force acting on you is gravity. That's the only force acting on you, and we call that weight. We give it a special label, W, force of gravity down, called your weight. If that object, we set it on a table, it stops accelerating. Well, Newton's law says for every force, right, you get an acceleration, and every object stays in motion unless acted upon by an outside force. So what would stop this thing from falling? Whatever it is, we call it the normal force. Okay, it could be the table, it could be your hand, could be the ground, could be air resistance, could be something. And not air resistance, because usually we consider the normal force to be a force perpendicular to the surface that keeps the ball from falling through the table. So we know every object has weight on it from gravity. If there's a table in the way preventing it, the normal force is going to equal the weight. Okay, the two vectors will be equal and opposite, and on opposite sides of the table. So this would be the same as if we added them up. The normal force minus the weight would equal 0 net force. So that would equal F. The sum of your forces would equal 0. You'd have 0 acceleration. Your thing is sitting there, sitting still. So anytime you have an object, if you're sitting here, you've got a weight, and you've got a normal force on you as well. Sometimes I write F sub n, sometimes I just write n. It's just in order to be standing on something, that something has to support your weight. Okay, so why do balconies collapse? That is when you have too many people partying, okay, on a balcony, and all of their weights. Okay, let's say this normal force, every time you add one, so let me draw this again. Let me draw it this way. Okay, we've got a balcony. We've got a person standing on it. There's the weight pulling down. Okay, the balcony says, okay, my normal force, balcony's holding up, compensating for that one person. Another person gets on, they have their own weight. Oh dear, now we have to make our weight twice, our normal force has to get twice as tall. Third person gets on, another weight. Oop, our normal force has to compensate for that person too. Doop. Uh-oh, fourth person, 1, 2, 3, 4. Doop, 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 doop. 1, 2, 3, 4, 5, right? And let's say that's the maximum that this thing can support. That's how much weight, you get on an elevator, it says 3,000 pounds maximum weight. That's what what is the normal force that the elevator can provide. Okay, you put one more person on, and it can't support it. It can't do it anymore, so boom, the balcony collapses, because we have the sum of the forces equals ma, and we could have, 6. We could support 5 folks, so we could have 5 weights minus the normal force equals 0. But as soon as we have 6 weight, when we minus the normal force, we get 10 newtons or something in the negative direction. So now we have more weight than we can withstand, and that's going to give us an acceleration. Boom, and we are going to drop like rocks. Okay, so that's how that works. When it comes to the normal force. The normal force is just whatever is supporting you from falling through a table. So here's an example with Bow Wow Chow. Bow Wow Chow, yippee. Okay, so when you have this Bow Wow Chow, okay, and they're showing before you set it on the table, you're applying the normal force, and there's the weight of the Bow Wow Chow. When you set it on the table, normal force and the weight are balanced by the table. Okay, so in this case, it's not the normal force, it's the force of the hand. You're lifting it. You can consider it a normal force if you would like. Okay, and there's your free body diagram. They're the same vectors because they are pointed in the same direction and have the same magnitude. Okay, now this is where it gets a little tricky, but it's not. So the reason we call it the normal force is because it's always normal to the surface. Okay, it's always perpendicular to the surface. That's what normal means. So if I have a surface like that, that is 90 degrees, that's perpendicular. If I have a surface like that, that's 90 degrees, that's perpendicular. If I have a surface like this, boom, that's 90 degrees, that's perpendicular. Okay, so normal force just means that normal force is always normal to the surface. And that makes sense. So where this gets tricky is on inclined planes, but it's not that tricky. Again, it's where's the right triangle? So this is your weight, okay? There's your normal force. All right, so what we usually do for these problems is rotate the coordinate system, so that instead of having a coordinate system that looks like this, and now your motion has x and y components, and your acceleration has x and y components, and so on. Instead of doing that, let's rotate our coordinate system so our x and y are here. Then, if you rotate, the video that you're watching, so that it's straight up and down, then like normal, then the only vector that's weird is your weight, and it's got 2 components. Otherwise, your normal force is in the y direction, your velocity is in the x direction, your net force is in the x direction. Everything's better. The only thing you care about is balancing out your normal force with the y component of your weight, which is called weight perpendicular here, and then the weight parallel component, or the x component, that's going to cause your acceleration down. Okay, so the way these work is simple. Okay, what you do is you say that once you have your coordinate system like this, and the x is along this direction, then what you want is the component of this weight that's actually going to cause you to accelerate, and that's this component. And so if that's your angle, that's the opposite over hypotenuse. So what you want is mg sine theta. That is your weight. That's what's going to cause you to accelerate. In this case, we got a little bit of a friction force we have to subtract off, but that's going to equal ma. If you want to know your acceleration, this is how you solve it. Mg sine theta minus f. Why mg sine theta? Because this incline has a 25-degree angle, And that's the same angle as up here. If I zoom in here, this angle is 25 degrees. It's the same angle as the incline. So if they ever tell you the incline is at 25 degrees, then you automatically know that this is 25 degrees too. That angle between the perpendicular and the weight straight down. So that angle is 25 degrees. This component of it is, if that's our angle, here's our right triangle, that's the opposite over the hypotenuse. That's SOHCAHTOA, that's sine. Okay, so we know that mg sine theta minus our force of friction equals ma. Turns out that the force of friction depends on the normal force. So the force of friction, if you want to know how much the force of friction is, it's the weight. It's your weight in the perpendicular direction times some coefficient. So it turns out we're going to have mg sine theta minus mg equal minus mg cosine theta to get our perpendicular component times this coefficient of friction, which we'll talk about. That's going to equal ma. So we've got our parallel component of the weight, our perpendicular component of the weight, and that will end up giving us our acceleration. So this friction, if you want to know how much friction you have, it depends on your weight. A heavier object has more friction. You probably understand. If you try to move a giant bookshelf, it's a lot harder to slide around on the ground than a vacuum cleaner or something. Okay, so that's what that is. We'll talk about that more. And here's your components there of that inclined, showing you a way to rotate your coordinate system, talk about the weight in terms of the component that actually does the acceleration, and this one that provides your force of friction. Okay, and there they are, mg sine theta, mg cosine theta. All right, so tension is another force that we use all the time, and most of the time you're ignoring some of the tensions. So for example, you got some guy, he's holding on a rope, there's a tension up and a tension down. That's not what we care about. We don't care about this other tension up here. We care about that system. And so the free body diagram here is going to be the tension up minus the weight down. And that's going to be the equations you use. Tension in the positive direction minus weight in the negative direction equals, in the case of if this force balances that force out, then you have no net force. Okay, everything equals 0. Those two vectors are the same, equal and opposite. Okay, and that's what they're saying here. All right, and then yeah, we've got some special problems here where we split everything up, and I think there's a better drawing of that down here. Okay, I don't know what this guy's doing, hanging around on a tree. Blah, blah, blah. Okay, so this is an example of a typical problem that people always have trouble with. So let's say you got a traffic light and it's hanging a little wonky here, and they tell you they want to know what's the tension in the cable or something. What's the tension in this cable? How much stress is that cable under? Well, the amount of stress in that cable depends solely on the weight of your traffic light. Okay, the weight of your traffic light is going to determine the tension in those cables. Now, the important thing is that these two ropes, there's tension in these here ropes. Okay, tension 1 and tension 2. The thing about these two tensions is that they have x and y components. There's the y components. In this case, T1, did I say x components? These are y components. These two y components, T1y plus T2y, are working together. They are pushing up. And they minus the weight equals 0. That's one of your equations. Boom. Because this component plus that component has to cancel out the weight. No other component is going to do that. Otherwise, this thing will snap and fall. Okay, so that's your first equation that you have to set up. You have to find the y components of these two tension vectors. What does that depend on? It depends on these two angles, right? And you can find those two angles. Usually they give you a distance, length here, length here, length here, something like that. And you can figure out either this angle or that angle. And then if you remember, one of the most important rules that we use all the time is that if that's your 90-degree angle, if you have this angle, let's say that's 15 degrees, then this angle is 90 minus 15. okay, because there's your 90-degree angle, and then the whole triangle inside has to equal 180. So then the sum of these two has to also equal 90, so that 90 plus 90 gives you 180. So that means if you know one of the angles that's not 90, you can know the other by subtracting 90 from it, okay? So what do? You've got tension in these here ropes, and you've got a y component there balancing out your weight, okay? That's one equation. The other equation, since this traffic light has no x component to its weight, then you know the x component of this tension and the x component of that tension has to be the same. So then you've got T1x minus T2x equals 0. That's your other equation. Between those two equations, you can get the tension in any rope. You can solve for once you know the tension, you can solve for the total tension, because the x component here is adjacent, so that's going to be T cosine theta is going to be the x component. T1 cosine theta minus T2 cosine theta equals 0. So there you go. That's no longer the component, that's the total force, T1. I just put it in terms of the cosine theta. Same thing here. You can have T1 sine theta minus T2 sine theta minus weight equals 0. So between those two equations, watch this, I can say that T1 is equal to theta 1 and theta 2 if they're different angles. T1 is equal to T2 cosine theta divided by cosine theta 1. There, I've got an equation for T1. I can take that, plug that back into this equation, and I can get that T2 cosine theta divided by cosine theta 1 minus T2 sine theta minus W equals 0. Now what can I do? I can factor out the T2's here. I can get T2 is equal to, T2 times cosine theta 1 over cosine theta 2, for example, minus sine theta 1 equals weight. Okay, so anyway, this is getting a little complicated. We'll go over this in class a little bit more, but read through that because it'll show you how to set these types of problems up. They're very straightforward. It's just learning the rules about how to solve this type of problem, but you have to solve these problems all the time, and it's easier, if you know how to do it now than when you try to do it on some entrance exam or when you're building a bridge or something. Okay, bloody bloody blah. Okay, now we've got, looks like a person trapped inside a rope-powered elevator or something like that. Okay, we got a man standing on a scale in an elevator. This is an elevator pulled up by a rope, okay. Calculate the scale reading, okay, if the elevator is moving up and if the elevator moves up at a constant speed. So if the thing is accelerating, that's going to be different than if it's moving at a constant speed. Okay, so try to work through this one. You're going to have this force down, and then, well, there's going to be a weight down too, and you got all of these things working together. Okay, so when you're accelerating up, you're going to appear to be heavier, and you should try and predict what that scale reading is going to be if you're heavier. All right, so these are just problems. Okay, there's a little bit of an end thing here on the 4 basic forces. So you've got the 4 fundamental forces of nature are gravity, electricity, and magnetism, the weak nuclear force, and the strong nuclear force. Gravity attracts masses together, so if you have 2 oranges, they're technically attracted to each other. The electromagnetic force is what causes magnetism and light and every other thing. The weak nuclear force is what causes beta decay and how nuclear reactors work. Strong nuclear force is what keeps protons together in the atom around other neutrons. That's what keeps the nucleus together. So that's why they call it strong. So the carrier particle, we think of the graviton as causing gravity. The graviton has not been discovered, probably will never be, maybe. It's so small. It's just so hard to measure. We might be able to infer it somehow, but electromagnetic, the photon, is the particle that does all that, magnetism and everything. These W and Z bosons are special particles that allow a proton to turn into a neutron, for example, and emit a neutrino and an electron.
and the gluons are the particle that glue the nucleus together. All right, so yeah, there's just a weird thing on forces here. This is a little bit out there, not going to make a whole lot of sense, but the idea is that there's force fields. So if you have two charged particles or magnets, you know that they act on each other at a distance. You know the moon is being held in place by the Earth, even though they're not in actual contact. So that's an interesting thing. Okay, see you guys tomorrow. Bye.